This is a lecture on classical wave mechanics. There are fundamentally two independent types of motion. We have irrotational motion, in which case the curl of the vector field is zero, and we have incompressible motion, in which case the divergence of the velocity field is zero. We can use a Helmholtz decomposition to take any vector field, but in this case the momentum density, so density times the velocity field. We can divide that into a curl and a gradient of a scalar and a constant component. So if we make these last two terms zero, we have incompressible motion with zero divergence and also constant density. So spin angular momentum density is the unique vector field in the Helmholtz decomposition, and it's the vector field whose curl is equal to twice the momentum density. Okay, so we've defined spin density as this field whose curl is twice the momentum density. And we also have angular velocity is half the curl of the velocity field. So we can use those to calculate the total angular momentum, which is the integral of the radial vector cross with the momentum density. And that turns out to be equal to the integral of the spin density within some boundary terms that fall to zero if the fields fall to zero as well sufficiently rapidly at infinity. We can also calculate kinetic energy, the integral of 1/2 rho v squared, and that's equal to the integral of 1/2 the angular velocity multiplied by the spin density, again within some boundary terms that we assume to be zero. Okay, so if we have some sort of Lagrangian density with 1/2 rho v squared, so it has a kinetic energy term in it, then the derivative with respect to the angular velocity we can take from this form of the integral, and the result is the spin density. Okay, the factor of 2 goes away because really you can calculate angular velocity from the spin density, so you have to differentiate actually both of these terms. Okay, so spin density is in fact the conjugate momentum to angular velocity. Okay, as an example, a rotating cylinder, the spin density would be a parabola, peaks at 0 radius and then falls to 0 at the edge. The velocity field is all azimuthal and proportional to the radius multiplied by the angular velocity. And then the angular velocity is constant out to the edge, at which point there's actually a spike going the other direction. And that defines the field. Everything's zero outside. Okay, and if we do the integrals, the total angular momentum comes out to be the usual moment of inertia times the angular velocity, and the total kinetic energy is the usual 1/2 moment of inertia times the angular velocity squared. So spin density gives the same results as ordinary angular momentum. Okay, so to summarize part 1, there is a classical analog of spin angular momentum density. It's the field whose curl is twice the momentum density. And if we translate that to quantum mechanics, we can say the quantum mechanical spin angular momentum is the angular momentum of the medium in which matter waves travel. And you can refer to that as the vacuum or the ether, whichever is your preference.